Hey, dear class, so section 10.4 is all about vectors. We are basically taking what we've been doing with the circle and polar coordinates now, and just instead of it just being an arbitrary point on a circle, or an arbitrary point in space defined with polar coordinates on a circle, we're basically going to connect the origin to that point and put an arrow through those two points. So it's like a direction instead of just a point in space. All right, there's all the different things that we're going to do in this section, and all we're talking about is two components: a magnitude, like how long the vector is, and a direction, the way it's pointing. So it's basically like somebody saying, where is such and such? Where is it? And somebody is pointing to it and telling you how far you have to walk in that direction to get there. All right, there's lines, like we've seen lines through 2 points. There's a line segment just cutting off going off to infinity on both ends and just stopping at those 2 points. But what we're going to do with a vector is basically a combination of those. So we start at point P, we go to point Q, and we put an arrow at that end rather than just a single dot. And it's not a ray. It's not, the arrow doesn't go on forever past that point. The arrow starts at P and it ends at Q. And that is the idea of a ray. All right, when we have the zero vector, it has no magnitude and it has no direction, because we're not pointing outward and telling you to go this far in this direction. It's basically just a point as far as the application. All right, if two vectors are equal, it means that they have the same direction and the same magnitude. They just don't necessarily start and stop in the same place. So I could have infinitely many of these, because if you see, I'm going up 1, 2, 3, and then right 1, 2, 3, 4. So any of these points, if I start here and rise 1, 2, 3, run 1, 2, 3, 4, I end up at that point, and that red vector is the same as this vector, and this vector. They're all the same vector. They're not starting in the same place and not ending in the same place, but that's not what a vector is. A vector is a magnitude and a direction. And these 4 vectors all have the same magnitude and direction. All right, when we sum two vectors, that's what we refer to as the resultant vector. And it literally means I started here, I went to here, and then I stopped and reassessed where I need to go, and then I walked in that direction. And then the sum would be, from where I started, where did I end up? So if, a sum of two vectors, if I start there and I go to here, and that was my first vector, that was my V vector, and then I turn from there and go down here, that is my W vector, then the sum would be that. It would just be where I ended up. So it is just a kind of a net position. After you did all the movements that you're going to do, all the directions and magnitudes defined by the previous vectors, the sum of them would be just where did we end up from where we started. All right, if you recall, the commutative property of numbers meant that I could add numbers in any order. 2 plus 3 is 5, 3 plus 2 is 5. Well, the same thing happens with vectors. It's just the geometry is a little bit different. If I start with V and add W to that, I went in this direction first and then stopped and turned and went in that direction. So I ran 1, 2, 3, 4 in rows 1 first, and then I ran 1, 2 more in rows 1, 2, 3. All right, so that is V first, then W. But if I did W first, that's running 2, rising 3. So running 2, rising 3, but it put me there, and then doing the 1, 2, 3, 4, and 1. But I end up in the same place, so their sums are the same. So W plus V, V plus W would give you the same resultant vector. And then the associative property of numbers, that if I'm adding these numbers, typically people just add left to right. So 2 plus 3 is 5 plus 4 is 9. What you did technically is you added these two first, and then you added the 4. But if I did it this way first, 3 plus 4 is 7 plus 2 more is 9. Again, I get the same thing. That was the associative property of addition, and it works with vectors too. So we get a resultant vector, so V plus W. So here's starting with V first, and then doing W second. So there's V plus W, and then add U to that. So there's V plus W, there's U. So the resultant would be from here to here. All right, and then if I had u plus v first, that would be here. There's u, there's v, so there's u plus v, and then adding w to that would move me up that way, and then that would be that vector as well. So it does, the order that we add vectors doesn't matter. Again, if this person is saying go in this direction, but only after you've gone in these two directions, it'd be the same thing as you went in his direction first with what this person said, and then added this to it. They're just arrows pointing us in directions. So whichever order we choose to do it, we would end up in the same place. All right, just again, like with numbers, there's something called the zero vector. If you add 0 to any number, you get that number back. If you add the 0 vector to any vector, you get that number back. So the 0 vector, a lot of times I'll put a little arrow on top to let you know that that's a vector. I typically do that with my vectors as well. Our textbook and the PowerPoints use bold font for a vector. So this is in bold, this is in bold, so those are vectors, but you'll see me put arrows on the top. And then there is a 0, so the idea in math, if you add opposites, 3 plus -3 gives you 0. A vector plus its opposite would give you the 0 vector, meaning if I went in the direction that this told me, I went 3 up and 4 to the right, and then went in the opposite directions, which would mean go 3 down and 4 to the left, I would get back to where I started. So this is like the resultant would be you didn't move. So vectors have opposites, and that literally multiplying a vector by a negative just completely switches the direction, 180-degree rotation of the vector. All right, and the difference to vectors is just negating the second vector and getting the resultant. So if v goes this way and w goes this way, well, that means negative w, if it would be the exact same length as w, but in the opposite direction, meaning I would rotate it 180 degrees. That's negative w. And again, it's a resultant. So it's connecting where I started to where I ended up with a straight line. And so that would be v minus w. All right, so that's the idea of a vector being subtracted from another vector. It's the same thing as adding the opposite of that vector. And the opposite of a vector is just making them like into a straight line. But the reality is we rotated. We rotated 180 degrees or pi radians to get there. All right, and then if we scale a vector, it just depends on how big the scalar is. But if the scalar is bigger than 1, we're making the vector longer, but not changing the direction. If we have a value that's smaller than 1, it's going to scale it down and make the vector smaller if it's between 0 and 1. And then if it's negative, it's going to scale it and rotate it if it's a negative number. So it's going to go in the opposite direction and either grow or shrink depending on that value, of the absolute value of that scalar. So there's some examples. So there's v, negating it, multiplied by -1, that's the same as the opposite of the vector. So that just switches the direction. But doubling it, I rose 2, ran 3. Now I rise 1, 2, 3, 4, and I run 1, 2, 3, 4, 5, 6. So I'm doubling my rise and I'm doubling my run when I double the vector. Now, there's just a few properties of vectors, like scaling it with 0, 1, and -1. So if you scale any vector with 0, then you're going to get the 0 vector. If you scale a vector with 1, that is that vector. And then if you scale it with -1, that gives you the opposite of that vector. We're just going to rotate the vector. All right, this is the distributive property. So if I have two scalars and I want to combine those together and then scale the vector, it's like scaling the vector with A first, scaling the vector with B, or beta, alpha and beta technically, and then adding those two vectors. So in essence, what I did is distribute. I distributed that vector in from the right side, and I get alpha times the vector, beta times the vector added together. And then this literally does look like the distributive property that you're probably more familiar with, coming in from the left side into the parentheses. So I'm distributing. Alpha is a scalar, v and w are vectors. So if I want to scale a resultant vector, I could just scale each individual vector and then get the resultant there. And then the same thing if I scale and then scale again. If I make a vector, there's the original vector. If I make it twice as long and then negate that, to make it go in the other direction, so that would be like 2, and then this would be like -1. Well, multiplying together would be like -2. And I could just do that all at once rather than in steps, basically is what that's saying. All right, now we're going to turn to graphing vectors, plotting vectors. So if I'm given a vector v and a vector w, so which I have here, adding them together again would be starting at the initial side of v, going to the terminal side, and then turning and going down this vector that w says, which is down 2, right 2. So down 2, right 2, I would end up over there, and I would have basically a straight line that connects me from there to there. All right, what if I have v minus 2w? So I start off in vector v. All right, there's vector v. W goes in, down and to the right. So minus 2w would go up and to the left. And because I'm doing it twice, I would go up 4 and to the left 4. So there's v, then I go up 4, I go to the left 4, and there would be minus 2w. All right, and then 2v minus w minus u. So double v, so that's 1, 2, 3 to the right, so now I go 6 to the right, up 1, 2, so now I go up 4. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. There's 2v. Minus w, again, that's going to go now left 2, up 2. So left 2, up 2, and then minus w, or sorry, minus u. Just going back in the other direction. So down 3, left 1. Down 3, left 1. So there's where I end up. And so I connect where I started to that point. That's the visual of the overall resultant of these 3 vectors. All right, when we see this, we're talking about the magnitude. How long is the vector? How, we're talking about I'm going 3 to the right and 2 up. But what does that end up being? Well, 3 to the right and 2 up, that's going to create a right triangle. Like when I connect 3 to the right and 2 up with that resultant vector, or with that combination of those, I get right and up. So that's 90 degrees. So it's going to be a right triangle. So the magnitude formula is going to be 100% based on Pythagorean theorem. Right, it's like absolute value, so it is greater than or equal to 0. It is a distance. It's the distance of that arrow. And your only way you can get, it says greater than or equal to 0. The only way you can get 0 is if you're dealing with the 0 vector. Right, the magnitude of the opposite of a vector is the same as the vector itself. So the direction that we're pointing it doesn't come into play here. It's just strictly the length of the thing. And then the magnitude of a scaled vector is the absolute value of the scalar times the magnitude of the original unscaled vector. All right, and then if we have a vector of magnitude 1, we call that the unit vector. So it's unit length, just like the unit circle. All vectors of unit 1 live on the unit circle. All right, and then notation. This is how we write the vector. So it kind of looks like point notation, and it kind of is point notation. So if this is the point AB, the only difference between that being a point and being a vector is I need to connect the origin to it. So as soon as I connect the origin to it, now that becomes vector AB rather than just the end terminal side of the vector being point AB. They have that kind of similar crossover notation for a reason. One is like where I'm ending up, and the other is if I were to connect the origin to that point, I would create that vector that terminates at that point. All right, notice this picture. It's bringing the x-axis into it. It's because we can talk about rotation off the x-axis to a vector and start getting into the polar forms of vectors. All right, but if our points are in space, if they're not connected to the origin like that picture that we saw here, if they are out in space, then we describe the vector by the change in x, the change in y. This is how much x changed. This is how much y changed. And if you're used to change in y, change in x, thinking about that as slope, as a ratio, that technically is. But when we're talking about with vectors, we're laying out just the horizontal change and the vertical change, and not taking it as a ratio, not dividing, which is what slope is. But when I was saying rise and run before, if you were thinking in your head slope, there's a reason. It's because this is very similar to slope when we're coming up with where my new position will be. So I'm just subtracting these values, and then I can, because vectors are equal, right? As long as they have the same change vertically and horizontally, they're the same vector. I can pick this thing up, stick it back down at the origin, and now I terminate at point AB rather than x1, y1 moving to x2, y2. It'd be the same thing as the origin moving to point AB. They're the same vector. So a lot of times we pick vectors up that are in space and move them back to the origin to give them their name, just to make it a little easier. All right, let's just do one with an example with actual numbers rather than the x1s and the y1s and all that. So when we subtract these, we're going to subtract the x's first. 5 minus 0 is 5, 6 minus 3 is 3, and then put those differences into its own vector. So that's going to be 5, the vector 5, 3. So there it is with the 2 points we were given, but if we pick that up and set it back down at the origin, it's going to terminate at those differences. So it's going to terminate at 5, 3, because that's the difference in x and the difference in y. That makes it easier to name the vector. When I say name it, I'm just talking about a single number in the x position, a single number in the y position. But we get those values from just subtracting the x change, comma, the y change. All right, some alternate notation here, because the I vector and the j vector are unit vectors. They are moving just in the x direction, moving just in the y direction, one unit. We can write any vector in space as that a vector multiplied by I, or that a magnitude multiplied by I, and the b vector multiplied by j. And this resultant vector would then be this much times I, which is going to move me in the x direction, this much times j, which is going to move me vertically. And so I would still end up at that same place. I would still end up at AB. So this is the alternate notation I was talking about. Instead of writing your vectors similar to that point notation, but with those order brackets, instead we use IJ notation. Okay, so that's when you hear me say IJ notation, that's what I mean. I mean, don't use the order brackets with a comma between them, similar to the point notation. Use the IJ vectors and add them together. All right, this is just showing you different things that we can do with vectors. So if we have, this is V, this is W, and so I have these two different vectors. There's the sum. I'm just adding the x components, so I'm adding this A1 and this A2 together to get the horizontal components of the new vector. And then I'm adding the b's to get those vertical components of the new vector. And then the same thing if I'm subtracting, I'm doing the same thing. It's just the second vector is being subtracted rather than added. All right, and then here's the really big one that's on this page. There's what we were talking about before, the Pythagorean theorem showing up in that magnitude formula. So if you square both sides, you would get the magnitude of the vector squared is that a1 squared plus b1 squared. Remember, a1 is our left to right, b1 is our up and down, and then that defines the vector, how much up and down we go, how much left and right we go. So there's v, there's a1, there's b1. That's a squared plus b squared equals c squared. It's just we solve it for the magnitude of the vector, and that's the reason why it's in that form. But that's how we get magnitude, just the Pythagorean theorem, which we've already used so many times this semester. All right, if we're adding vectors, we're just going to add the I components, we're going to add the j components, and simplify. So there's the sum of the two vectors. We regroup, put the 4 and the 2, not this 2, but this 2 together for the i's, and then this 2 and this -3 for the j's, and so that's 6i minus j. It's just basically adding like terms, and your i's and your j's are your x's and your y's that you've seen before when you did like terms. All right, if you want to use not the ij notation but that like point notation, just adding the first components and then comma adding the second components. All right, subtracting, just remember you got to distribute these through, so it becomes a -2i and a +3j. So just watch your signs. Subtraction is always a little trickier just because of that distributive property for that second set of vectors. All right, we can also do it this way. Just remember to negate the 2 and the -3 and get a -2 and a +3. So that's going to be the 2, 5 vector. All right, when we double a vector, literally we're just going to double the components. So 2v is going to be double 4, 8, double 2, 4. And that's the way that we can do it. Again, ij notation or the other notation. Tripling vector v, that's going to be a 12 and a 6, and then negating these two and doubling them, and then combining. So there's tripling vector v, negating the 2i, doubling it, negating the -3j, and doubling it. So it's going to become a +6j, and then combining those together. Again, we can do it with the alternate notation. Just multiply the scalars on the outside times the components on the inside, and then just watch your signs with that minus sign. All right, then how do I find the magnitude? I square the first component, I square the second component. So I square the 4, I square the 2, and then I add those and take the square root. So that's the square root of 20. And then just simplify. You're going to have to simplify these. So 20 is divisible by 4, which is a perfect square. And so the square root of 4 is 2. And that leaves the square root of 5, which was not a perfect square, inside the brackets. Or the square root symbol, inside the square root symbol. All right, now we're going to look at finding a unit vector. This means that we need to find a vector that's in the same direction as the original vector v, but has unit length. And the way that we do that is we just find the magnitude of vector v and scale it down, divide it. And when you do that, if you recall, the magnitude of that vector will be the magnitude of the scalar outside times the magnitude of the original. Well, the magnitude of the original is this symbol. So when we divide it by this, we get a magnitude of 1. All right, and then just multiplying both sides of this equation by the magnitude of v, you get a vector can be written as a unit vector in its same direction times the magnitude of that vector. And that breaks it down in the two terms, the two pieces of what a vector is. Its direction, which is the unit vector, and its length, which is the magnitude. All right, how do I find this unit vector? Well, the first thing I need to do is find the magnitude of v. And then once I find the magnitude of v, I square the 6, I square the 8, add those together, take the square root. 36 plus 64 is 100. The square root of 100 is 10. And now I'm going to divide the 6 and the negative 8 by 10. All right, so that's going to look like this. So 6 over 10 is 3/5. Negative 8 over 10 is negative 4/5. And so there is my unit vector. So if you give me a direction of a vector, you are basically on the unit circle, and the angle there is how much I've rotated off the positive x-axis. And if you scale that up, you multiply that by the magnitude of v, then you're just going to scale that unit vector up to whatever the length is, and make it longer or make it shorter. Again, it could be a fraction, but that's going to give me a vector that goes through again, if it's longer, it goes through that unit circle and comes out of it, but it's pointed in the same direction as that unit vector. All right, this is just r cosine theta plus I sine theta. This is just like the polar version of a complex number. No different. It's polar coordinates, defined by an angle of rotation. All right, so we're making we're throwing a ball. It's got an initial speed of 30 miles per hour, and it's making a 45-degree angle with the positive x-axis. So there's the positive x-axis, 45 degrees, roughly around there. And then this initial speed that they're giving us literally is the magnitude of this vector. So this is our vector v up here, and the magnitude of this vector v is this 30 miles an hour that they're giving us. And so the question is basically wanting to know how much of this 30 degrees is in this upward direction, a vertical vector that's a component of that overall vector, and then how much of it is in the horizontal direction initially when that ball is being thrown. So basically it's having us break this into the components in this form. So this is going to be 30, the magnitude of v, and then the alpha, the angle, is 45 degrees. So because it's 45 degrees, cosine and sine are both the same. They're both the square root of 2 over 2. And then multiplying that, the 2's are going to cancel with a 30 in both positions. We're going to distribute this through like we were talking about before. And the 30 both times will get divided by 2 and give us a 15 square root of 2 in both directions. So because of that, that is the speed in both the vertical and horizontal directions. So if this had been any other angle, all you would have done is right there evaluate the cosine of 30 degrees, sine of 30 degrees, cosine of 65 degrees, sine of 65, whatever that angle is, and then multiply the 30 through. All right, and then find the direction angle. So what is alpha if this is my vector? So 6i, 3j. So there's my origin. I'm moving 6 to the right. I'm moving 3 up. So something like that. There's my vector, and it's wanting to know what is this angle that they're calling alpha. So all we have to do in this case is come up with a trig function. Just again, it's right triangles that would define that angle based on the side lengths I know. And because this is 6 right here, the adjacent side is 6, and the opposite side is 3, I can set up the tangent. Opposite over adjacent. So tangent alpha is a half, I can use the inverse tangent to solve that since it's an acute angle, and I get 26.6 degrees. All right, so we have to account for it going all the way around the circle. So inverse tangent's not always going to work. Inverse tangent would be fine if we were in quadrant 1 with an acute angle, but if we're in quadrants 2, 3, 4, inverse tangent can't get us into those angles. Remember, inverse tangent will get us in quadrant 1 or 4 if it's a negative angle, but because we need to be positive for this application, if we're not in quadrant 1, we're going to have work to do. So just keep that in mind. All right, and then here's an application of this. So when we model things in motion, a lot of times we use vectors. So these airplanes are moving due south, it says, and they are flying at 550 miles an hour. And then these arrows, the jet stream, the wind speed that is pushing in this northeast direction. Right, northeast is 45 degrees in quadrant 1. Okay, so there's north, there's east. 45 degrees northeast would be that 45 degree angle in quadrant 1. So there's a visual, and it wants us to find the velocity of the 737 relative to the air and the velocity of the jet stream in terms of I and J. So we need to come up with that first, and then find the velocity of the 737 relative to the ground. What if you're looking up at it? What are people seeing the resultant is? Moving downward this way with this wind blowing it, it's going to kind of push it off course a little bit. And then because we're getting this is moving down this way, this is moving northeast, we're going to be kind of moving in this direction. So we're getting a new vector. So this 550 is the direction it's wanting to head, but the resultant is this pushed to the kind of the east direction because of the wind, and that's creating a new vector. So this is asking us to find what is that new vector, and then what's the magnitude of that new vector. So part A, there is our vector for the wind speed, because we're doing north and south on the y-axis, east and west on the x-axis. Negative 450 due south is going to be negative 550j for that vector. And then the ij for this one, this is 80 for the magnitude, and then 45 degrees, so we just use cosine and sine of 45 degrees to get the magnitude of that wind speed. So 80 cosine 45, just like before, we're going to distribute this through and get 40 square root of 2 for both the I and j components. So that is the vector for the wind speed. That's this one right here in terms of I and j. And then what's the overall velocity of this thing? What is the speed that this thing is moving relative to the ground? It's just the resultant of these two vectors. So add them together. There is no I component for the jet's initial travel, like the vector that's describing the motion of the jet. So that I is just coming from the wind speed. And then the j, this doesn't have a square root, this does. So all we can do is kind of write it like that, unless we wanted to approximate both of these values, which is common for these applications. All right, then the actual speed, we're taking the magnitude of the I vector, the magnitude of j vector, so we're squaring these, adding them together, taking the square root. So doing it on a calculator, you get something in that ballpark of 497 miles per hour. So the wind, because again it's a headwind, it's pushing it not with the direction the jet's wanting to travel. It's kind of decreasing that overall speed a little bit. All right, and then if we want to find the actual direction, that's my y component, that's my x component. Remember, tangent's y over x, so we're taking this, dividing it by this, and again using inverse tangent, because again that is not a that's not going to be a quadrant 1, 2, or 3 angle. It's going to be quadrant 4. So inverse tangent will give us a negative angle. So we just need to understand where, what angle this is going to be. So this is again where the plane is heading. The wind is pushing in that direction. So this negative 83 degree angle is relative to the x-axis. Okay. But if I wanted to give a bearing, I need to go south and then east, however many degrees. So I would actually need to find this angle, how many degrees east that is. And so we can easily do that. That's 90 minus this number would be 6.5. So south, and then we move off of that 6.5 degrees to get the actual bearing that this thing is on. All right, this example, it's asking us how much does this piano weigh if it's taking this force to push it up the ramp. So if you look at it, that force, that 350 to push it up the ramp, is the magnitude of this F2 vector. And what they're asking, how much does the piano weigh, that's the F1 vector. That's the one that's pulling this thing straight down towards the center of the earth. That's the force of this straight down. That's the weight of the thing. All right, F3, that vector is just the vector that's keeping it, the force that's keeping it on the ramp. But it's the force pushing it up the ramp and the downward force that is ultimately the weight of this thing that we're being asked to use here. All right, this is 20 degrees, it says, the incline of the ramp. That means this is going to be 20 degrees. And the reason is because this is a 90 degree angle, and this motion right here to push upward is always going to be opposite the orthogonal, I should say, to the force keeping it on the ramp. So to go up the ramp, keeping on the ramp, those forces are orthogonal. This is a hypotenuse, and because this is 90 degrees, this is 90 degrees, this is the force to keep on the ramp, this is the force to go up the ramp. That inclination right there is the same as the inclination of the ramp. And that means these are going to be similar triangles. Right, and because now we know that this angle right here is 20 degrees, this one right here, the ones that we're looking for again are F2, that's the one that we know, that's the force that is pushing it up the ramp, divided by the hypotenuse. So that's opposite hypotenuse, that's going to be the sine function. So the sine of the 20 degrees is the force that I was given divided by the force I'm trying to find here. So that's the 350 is keeping it, pushing it up the ramp. F1 is the one I'm looking for. So I can do some rearranging, multiply by the magnitude of F1, divide by the sine. That's the same thing as multiplying by the cosecant, but you can type this into your TI calculator. Make sure you're in degree mode or put the degree symbol there, and you get about 1,023 pounds is how much that piano weighs. All right, but again, just look at what we did. There's the force that they're using. We're dividing by the sine of the incline of the ramp. That will give you how much that thing weighs anytime that you need to do anything like that. All right, static equilibrium, when you get to this, these types of problems, this is important. The sum of all the forces acting on the object is 0. The resultant is 0. So for this object to be sitting here hanging, the downward force of this 1,500 pound object has to be equal to the sum of these two forces that are pulling up to maintain, for that to be able to hang there. So these two forces, call this like, I guess just like left to right, F1, F2, and F3. All right, they're going to be written as vectors, but the magnitudes of these vectors need to add up to 0. Or the, this one is in the opposite direction of these two. So think of this one as like a minus the magnitude. But they would have to combine to 0 for this to be able to just hang there. Otherwise, if it wasn't 0, this would either be being pulled up or being lowered. All right, so we know this is 60, we know this is 45. We can come up with any of these angles required to come up with the names of these forces, again, relative to the positive x-axis. So this is 60, but if this is 45, that means this is 135. All right, so that first force we looked at, it's magnitude times the cosine and the sine of 135 degrees would give us something in that vicinity. Again, this is an unknown quantity, so we'll have to solve for it in just a little bit, but we know that the I component's negative, the J component's positive, because it's to the left and up. All right, for the second vector, we got that 60 degree angle, so we're going to do the same thing, cosine of 60, sine of 60, and then multiply that magnitude of the F2 in there. So there's the second thing we know. And then we know the third one, it's just downward, so that's negative 1500 J. So it's got an opposite sign of the vertical components here for these two. All right, and then the sum of these three forces need to be equal 0. So there's the F1 force, there's the F2 force, there's the F3 force. It's kind of like this. All right, there's F1, there's F2, and then there's F3. All right, remember, if the sum of the vectors is 0, then that means each component is 0. So that means this I plus this I plus, there is no I in this third one, but these two have to be 0. They have to cancel each other out, as do the J's. That's the only way we can get the 0 vector, is if both components are 0. So this plus this minus this. The I's have to be equal to 0. The J's have to be equal to 0. So end up with two equations. and we end up solving this system of equations. And this is something that you did in either high school math or pre-calculus math, these two equations that you get. And you can, basically you can, if you wanted to, even treat like the magnitude of f1 as x, the magnitude of f2 as y. So this is something times x plus something times y, sometimes x plus something times y minus a number. This is just a linear system of equations, and you're solving for x and y. So it's something you've done before, it's just we're using vector notation now. All right, so doing the algebra, we get this, so that gives us what the magnitude of f1 is. We can approximate that. It's about 776.5 pounds. And then once we know f1, we can use this equation that we saw earlier and replace f1 with this number multiplied by the square root of 2, and that gives us f2. All right, notice that when we did this multiplication, we went back to this, the exact, rather than this rounded version. Okay, I'm rounding here, and if I plug this in there for the rounded version, I would be rounding twice. And when you round multiple times, you bring error into the approximations. You bring more error into it. So use your exact values when you can when you solve these systems. All right, and that gives us the tensions on both of these cables. We're trying to find the magnitudes of F1 and F2. Those were the tensions, and so that's what we needed to do to get the answer to this problem.